In this video, we'll discuss interfacing with a microcontroller and other discrete components. We'll learn about pull-up and pull-down resistors, some of the internals for the general purpose digital input-output, and finally we'll talk a little bit about connecting a keypad matrix to our microcontroller. Let's first do a quick recap on digital logic. With digital logic, we use a high voltage to signify a 1 and a low voltage or ground to signify 0. Now there are a variety of digital logic families which use different types of devices and circuits to implement digital logic, and historically there's been a wide range of digital logic families. Today, CMOS technologies are by far the most common approach for implementing digital logic. And a simple circuit we can use to represent CMOS logic is something you've all seen before, which is an inverter. The CMOS inverter is implemented with two MOSFETs, one PMOS and one NMOS transistor, with the gates tied together and connected to the input, and the output coming from the net between the transistors. So let's assume our VDD is 3.3 volts, which is a common supply voltage in what we have for the MSP432, at least one of the configurations. And let's say we have a high voltage, a logical 1 on the input. This would result in a channel forming in the N-type device between the drain and the source, allowing current to flow from the output to ground. While the PMOS device would be in an off state with no channel formed, meaning the output would be pulled low and I would see a 0 on the output, the inversion. Conversely, if I put a low voltage on the input and A was connected to ground, a channel would form in the PMOS device, while the NMOS device would act as an open, and current would flow from VDD through the PMOS to the output A0, and I would see a high voltage on the output. Now, as you've probably also seen before with digital logic, we also can expect some noise or variations in the circuit, or when we attach loads to our gates, we see some loading effects, resistive loading, capacitive loading, which will result in a voltage not necessarily being entirely at VDD or ground. But this is one of the beauties of digital logic design, as these circuits are designed such that as long as a high signal is above some threshold less than the high voltage, say this is 3.3, so for many logic families this might be around 2.2 volts, and a low signal, as long as it's not larger than some value around 1 volts, we'll also correctly interpret these as low or 0 signals, or interpret them as a 1 signal, with a certain range in the middle being illegal, and a region which we design our circuits to avoid. Now, different logic designs, whether we're talking about TTL or CMOS, will have different acceptable ranges. One other note here is that we can design logic to have either positive or negative logic, meaning that true is interpreted as a high voltage with positive logic versus negative logic, a true would be interpreted as having a lower voltage. This is sometimes also called active high or active low. Okay, so now coming back to the MSP432 and microcontrollers, remember general purpose input-output interfaces or circuitry is an important part of their design and how they can interface with a variety of different types of components and systems outside the microcontroller. In the case of the MSP432, it has 67 pins and 10 ports in total. If you look up in the datasheet towards the end, you'll find some nice block diagrams showing you the actual logic for each of the general purpose input-output ports. And remember, one key configuration is the DIR control register, which allows the same pin to be used for both input and output. Two tri-state devices or buffers, when DIR is set to 0, this tri-state buffer on the top is enabled and the processor can read what's on the pin, versus when it's set to 1, the DIR signal, this tri-state buffer is activated and whatever's in the register out is allowed to be connected to that output pin. Okay, so now let's talk about a couple key limitations for microcontrollers input-output, and specifically let's talk about the MSP432 limitations. So each of the GPIO pins has a limit on how much current can be synced or sourced from that pin. And so this, when we talk about the current that can sink, this is when the circuit is in a state where current is flowing into the pin and into the GPIO, and when its source is current, when current is flowing out of the pin into that external circuit from the microcontroller. In both of these cases, for the majority of the GPIO pins, when they're not set into a high drive configuration, the limit is actually, this slide is wrong, should be 6 milliamps. A couple of the pins can support the higher 20 milliamp limit, but the majority of the pins, when you look this up in the data sheet, their limit for sinking and sourcing current is 6 milliamps. There is also a constraint in total for across all the pins, which you also have to be careful with. And this is something around 50 to 100 milliamps. For the low voltage CMOS devices that are used for the GPIO pins, you can also look up in the data sheet and see that the maximum value that the output voltage can be when it's a low signal, when it's sinking current, is 0.8 volts. That's what we can expect. And when it's a high output, the minimum that we could expect the output of the voltage to drop down to is 2.2 volts. So now let's talk about one really important component that comes up a lot in different types of systems, which is a switch. And there are different types of switches, but here let's just talk about the basic switch that we usually use, a 2-pole single throw. Now, you might say, why can't I just connect that switch directly to the pin, with one end of the switch connected to the GPIO and the other end of the switch connected to ground? Well, when the switch is closed and I read that pin, I'll read ground, and that's okay. But when the switch is open, this net is now floating. It's not connected to anything. It's not being driven high or low. And this can be a big problem. Remember, our CMOS logic is built to be robust. It can tolerate some noise in the signals. But in this case, it's not clear, depending on the temperature, the noise, and the circuit, what voltage the switch is going to go to. And worse, this could consume a lot of power having floating pins. And even worse than that, this leaves that circuit susceptible to electrostatic discharge, which can permanently damage the devices. For this reason, it's always a good idea when you're not using GPIO pins on the microcontroller to put them into a non-floating state, either setting them as outputs or connecting them to a pull-up, pull-down resistor, which we'll talk about in 1 second. And you've all probably seen a warning when you've compiled Code Composer Studio about having pins left in this state. So instead of connecting the switch directly to the pin, the way that we connect switches to microcontrollers is with a pull-up or pull-down resistor, shown here. So with positive logic, when the switch is closed and I read the voltage at the pin, I'll see I have a high voltage. And when the switch is open, the net will be pulled low and I'll get a low voltage. This way I avoid the issue altogether of having a floating pin, and my pin is always in a good state, having a high or low voltage. And the same thing is true for the diagram on the left. I can use negative logic, where when the switch is closed, the microcontroller will interpret that as being a low voltage, versus when it's open, we'd see a high voltage. So many microcontrollers, including the MSP432, also have internal pull-up and pull-down resistors, because this is such a common part of many external circuits. And so we can use either an external pull-up or pull-down resistors, or we can also enable the pull-up resistors, and this is where the REN control register associated with the port is used to enable those pull-up resistors, and you'll be doing that with the keypad in assignment 4. Note that the REN resistor enable control register just turns on or configures the pull-up, pull-down resistor. The value set within the out register will actually configure whether it's a up or down resistor connected to ground or VCC. The other very common component that we connect these ports, and you've already seen this one as well, are LEDs. So just a quick review on LEDs. These are a special type of diode device with a typical forward current of around 10 milliamps and a forward bias voltage of 2 volts. Now there are different ways that we can connect LEDs to the microcontroller. So we can use an external buffer, shown here. We could also use a BJT to connect the LED, as shown on the right here. Depending on the currents that you're designing the circuit for, as well as the logic family or the device characteristics from the microcontroller, you might want to use one of these approaches. In general, these would help to limit the current and protect the pins on the microcontroller. If you're careful though in designing the circuit, we could also connect the LED using a circuit like this. And so with the MSP432, we can just connect our GPIO through a resistor to that LED going to ground. And then choose our resistor based on what we know the forward bias voltage and current is through the LED. In this case, 1 milliamps, so we can use Ohm's law to calculate that we need a 1.7 kilo ohm resistor to connect that interface. And note that this circuit on the left would be an active high circuit. When we drive or set the output in that pin to 1, the LED will turn on, and we send it back to 0, the LED will turn off. On the right side, here we have another circuit that has a larger voltage, say 5 volts coming in its supply, and we're designing this to have 10 milliamps of current. Then we can do something like this, and we would select a smaller resistor. So although this is a really simple circuit, it comes up a lot in many different applications. This is an example of a product for a glove sort of flashlight that uses the same basic circuit. There are also a variety of other discrete components and packages which you can use and implement within your systems. We've already seen in our earlier courses how we could use things like 7-segment displays, which have a package of LEDs in a certain pattern. And there are many other devices as well. The 74HC245 chip has 8 buffers that can be used in your design. We have latches, registers, and many other components. So one other quick feature here that you all hopefully have seen before in 233 or other courses is this phenomenon of switch bouncing. And this is especially a problem for push button type switches, where when the switch is closed, we don't get a clean signal going from low to high or high to low, and instead see these oscillations during those periods. And there's different ways to deal with this bouncing, but the way that most microcontrollers, including the MSP432, deal with this, and in general this type of noise or oscillation on the signals, is by incorporating a Schmitt trigger. And basically what this means is that that buffer within the GPIO circuit has a different point for transferring from low to high and high to low, allowing for that intermediate oscillation or bouncing to be smoothed out. And so if you look up in the datasheet, you'll see that all the GPIO pins on the MSP432 also incorporates a Schmitt trigger. So one other quick thing to note here is that although we have 10 ports on the MSP432, there are sometimes cases where we have many different types of devices and need to share those ports for different types of external circuits and functions. And so we can handle this with something called port multiplexing. And what this basically looks like then is we have a bus connecting from one port, sending the data to all the potential devices that we might want to at a given time. And then another port has individual enable signals that go to each of the devices and will select which particular device we want to access at a given time. Okay, so finally let's talk a little bit about assignment 4 in the keypad. So other than the buttons or the physical part of the device, there's actually nothing too complicated about the circuit of the keypad. It is a 4x4 matrix with 16 different switches. Now the way that you can use this is by connecting each row and column to its own GPIO pin, and we'll pick either the rows or the columns. You can use either one to be connected as an output port, and the other direction to be inputs. Now all the inputs will have a pull-up resistor connected, as we were discussing earlier, and we'll read in the other direction to see if any key has been pressed. And we'll know this if any of those inputs have a low voltage. So in the case that the rows are our outputs, the columns are our inputs, all the columns will have a pull-up resistor connected, and all the rows will first drive low, and we'll read the columns, and if any of those columns come back as having a 0, we know that a key was pressed and shorted that column to a row that's being driven low. Once we know that a key was pressed, we'll then in software go through a sequence of operations to determine which specific key was pressed. So we'll set each row, drive each row one at a time low, read the data from the input columns, and if at any point we see one of those bits as being low, we'll know that that was the particular column and row that had its key pressed. And so that's shown in the flowchart here at the end, and because that table has a fixed layout, we can get the corresponding character from a table once we complete the process.